Okay, cool guys. So today we are going to study about BFS and Dijkstra. BFS, which is breadth first search, and Dijkstra. So we'll be talking about the concept and the usage. We'll also talk about where to use it and where to avoid it. So a lot of people actually know that where you should be using BFS and Dijkstra, right? So people would say whenever you have to find the shortest path or you have to do a level or traversal, right? So you'll be using a BFS, or for the shortest path you'll be using a Dijkstra. But not a lot of people know that way not to use it. Then we'll be talking of the modifications that are required for CP. Now, obviously, you can use the standard Dijkstra algorithm with some pretty minimal modification at a lot of places, but there are some extra things that are being used in Dijkstra that are not relevant in most of the CP questions. So I'll be talking about that also, because there's no point in coding some extra lines when a shorter solution is available. And then we'll talk of a few great questions which I myself find awesome, and they were asked in some recent contests as well. So we'll be talking of them. So let's get started with the explanation first. So I hope before you started watching this video or you came to the session, you have actually gone through the previous video that talks about graph traversals and graphs in general. So with that knowledge, we can proceed further to what a BFS is. So let's say these are my nodes, right? So these are the nodes I am having. So let's define levels first. Now, since BFS is also called level order traversal, right? Okay, this is called level order traversal. So let's define what levels are. So the node I'm currently standing at, let's call it node 0. So this would be my level 0, right? Then I would only travel one unit from this node, right? So I'll travel one unit from this node over here and one unit from over here. So I'll reach the nodes, let's call them 1 and 2, right? So 1 and 2 are at level 1, right? Now from 1 I can go to 2 and I can go to this other node, let's call this 3, let's call this 4, let's call this 5. So from 1 I can go to 2 or to 3, but 2 is already traversed, right? So let's just go to 3. From 2 I can go to 1 and 4. 1 is also already traversed, let's go to 4. These two nodes now, the two nodes 3 and 4, they would be called level 2, right? Because they are at distance 2 from the root node. Now I'll try to again travel something. So from 3 I cannot go to anywhere. I can just go to 1 and to 4, both of which are traversed. I can only go to 5. Now 5 would become the level 3. Now a level order traversal would mean that in my first iteration, or in my first loop or first iteration, you can say, I'll be at the root node or at my level 0. Or let's call this 0th iteration, makes more sense, I guess. We'll be at the root node, level 0, that is root, right? In a second iteration, we'll be at level 1. Level 1, that were the nodes 1 and 2. In the third iteration, we'll be at level 2. That would be nodes 3 and 4. So yeah, 3 over here and 4 over here. And in the fourth iteration, we'll be at level 3. Okay, so if we called it 0, we'll call it first, second, so on. It doesn't matter actually. But just to make the concept more clear, let's call it this way. So yeah, in the third iteration, we'll be at level 3, wherein the only node we are having is 5. So up till this point, there's any doubt? Or everything's clear?
Yes.
Cool. Okay. So yeah.
Yes, sir. Clear.
Cool. This was the basic stuff. Now let's move ahead. Now how would we do that? So I can say that initially I'm having some kind of data structure. I don't even want to think about what data structure this is, but some kind of data structure wherein I only have 0, right? So 0th node I was having. Then in the second iteration, I want 0 to be removed, right? And I want these to be added. So I want 1 and 2 to be added, right? Now in my third iteration, I want 1 to be removed and 2 to be removed and 3 and 4 to be added. Now let's look at this in a better manner. So what I'm saying is, in the first iteration or in the 0th iteration, you're just having node 1 in the data structure. So this is the data structure I'm having. In the first iteration, you are having 1 and 2. In the second iteration, you are having 3 and 4. And in the third iteration, you are having just 5, right? Now you can say that we can do this via vector, we can do this via stack or a queue, or ample number of data structures available, and that's true. But how would we actually code it up? So I'll say that, okay, remove 1 and add 1 and 2. So that's cool. That's easily doable because there was only a single element. I could have easily removed it and added 2 elements onto it. But how would I add 3 and 4 from this structure? So the way it would have happened is that I'll go to 1, right? I'll check what all your neighbors are. So one would say that I am 1 and my neighbor actually is 3. So we'll say good enough. So I want to remove 1 and add 3. So how would we do this? If we do it via vector, right? So the removal itself would take us order of n complexity, right? And let's say we do n removals in total in the entire algorithm. So the complexity becomes order of n square, right? So this is not a good way of doing that itself. So what data structure would be the most beneficial if we have to remove the things from the start and add the things at the end? So we'll be adding 3 over here, right? So what data structure kicks in over here is actually called queue. I hope everyone knows the basic. So I can utilize the queue over here in each iteration. So the basic algorithm would over here would become that initially take a queue, push the root onto it, right? Then start an iteration. So till what time would this iteration keep on going? So it'll keep on going till the time there's some element in the queue. So till the time the queue is not empty, right? Not of queue of empty, right? What I'll do over here is firstly I define the size. So the size is q dot size, right? And I want that in my single iteration. Now why I'm taking the size over here? Because I know that in my current in my queue, let's say this is the level I, right? So at my level I am having nodes A, B, and C. So I want to process all of these 3 nodes, right? So I want to run this loop 3 times. Hence I'm taking the size over here itself, right? Then I'll say while this size is something, right? So till that I'm able to remove all the nodes from it, what I'll do is I'll select the node. The node would be the front element itself, right? After that, I'll say let's just pop the front element. So we'll pop it. And then whatever elements are there in the adjacency list of this node, add them to queue, sorry, add them to queue if they are not still processed. Does this make sense? And yeah, this is the entire BFS structure. Does this make sense? Because this is like 50%
Uh,
of the work. Yeah.
I got confused in the implementation.
In the implementation. Okay, cool. So what we are doing is that let's just talk of a very simple graph. Now this is the graph I'm taking. Let's make it a
Okay.
bit bigger. Let's make it a bit bigger. Okay, let's say this is the graph I'm taking. So
Let's take a binary tree now.
which one? This one.
A binary tree.
Let's take a binary tree. That's what you're saying.
Yep.
Okay, look, cool. No worries. We can take a binary tree also. So let's say this is the node 1, right? This is the root node, right? This is the second node. This is the third node. Make sense? Let's
Yep.
say this is the fourth node just to make it more complicated. Okay. So initially you'll be pushing 1 to the root. Then you'll say that while your queue is not empty, do this. So yeah, your queue is not empty. Your queue currently has one of the elements, that is 1, right? Then you'll say what the size is. So the size is also 1 because it has only one element. So the size is also 1. So you'll run this particular loop 1 time. So this will run 1 time, right? Then you'll say what's the
Yeah.
node. So what the node would be the front element of the queue. So this is the queue. The front element is also 1, right? So you'll say, okay, the front element is 1. So I'll say remove that. So you'll say, okay, I'll remove it. The element got removed. The current queue now is empty, right? Then you'll say what are the adjacent nodes to it. So the adjacent nodes to 1 are 2 and 3, right?
Yeah.
Now you'll say that if your 2 is present or if your 2 is actually processed, then don't do this, else do this. So your 2 is not processed as of now, right? You can store that in a boolean vector or wherever you want. You say it's not processed, so let's push that onto the queue. So this was the queue, you pushed 2 into it, right? Then you came again over here. Then you said, are there more elements that are in your concurrency list or which are adjacent to you? it said, yeah, the 3 is another element that is in my adjacency list and it has not been processed. I'm like, cool enough, push that also. Cool. So after this loop, you would have 2 elements in your queue. You'll go over here till that at this time your size was initially 1, this would have become 0. So yeah, this won't be processed again. You'll come out of this loop. You'll come back over here. Okay, let me draw it with this one. Okay, you'll come back over here. You'll say, do you have some elements in your queue? If your queue is empty, you'll say, no, my queue is not empty. I'm actually having 2 elements that are 2 and 3. Cool enough. And
Yeah.
at this time, this is the second time you're running this loop. So technically, you are at level 2 if you're taking 1-based indexing, or at level 0 if you're taking 0-based indexing. Now again, you'll proceed in the same fashion. Firstly, you'll say, what's the size? So you'll say, okay, so size is actually 2. So I'll have to run this particular loop 2 times, right? So in the first iteration, you'll say that I'll take the first element of the queue. So the first element over here is 2. So you'll say, okay,
Oh wait, I get it now.
what was the doubt actually?
Huh?
What was the doubt?
I didn't get how it was working.
Okay, got it. So basically, the entire intention is that this is the queue you are having, right? So whenever you start this particular loop itself, in the inner while loop, there would be a queue with X elements, right? I want to
Yep.
process all the X elements.
And while you're processing them, you'll also get their adjacent values
Right, and when I'll
for
be
the
having,
next iteration, right?
yeah, good point. Actually, I'll definitely explain this a bit more. So what's happening is that you are having these elements, right? Let's say A, B, C, D, E. You already know these size, right? So you'll say I'll process these elements, but while you're processing these, your queue would get extended, right? So you'll be having some neighbors of A, neighbors of A, neighbors of B, could be some more neighbors of B and stuff, right? But you don't want
Yep.
that in this particular iteration itself. You don't want to process these elements per se, right? So that's why you say that I'll be running my loop only size times. So I'll only be processing these elements in the current loop, so that I can say that in level I, or in current level car, I only process these elements, right? Make sense?
Yep.
Cool. Anyone else has a doubt in this?
Actually, why are we not keeping the track of visited nodes actually?
No, we are actually keeping this track of visited, and I explained it over that. So give me a second. Okay. Okay, over here I said that
Visited nodes queue में है ना?
no. So the problem is that visited nodes would not always be there in the queue, and secondly, you won't actually process your queue itself to check what all nodes are visited or not, right? So you'll have to keep a track of the visited nodes too. Over here, I said that if they're not processed, right? So when I'm
Got it.
saying if they're not processed, so you'll have to keep some track, right, of it. And the best way of doing that is through a visited array. So that would be that I'll explain when I'm implementing it. Make sense?
Okay, got it. Got it.
Okay, anyone else? Cool. Let's look at the implementation if no one has a doubt. I'll be looking at the implementation now. Let me just start coding from the scratch itself. Okay. So let's try to analyze how we did it earlier, right? Let me remove this and remove all the gibberish. So yeah, let's start from the very basics. So initially I want some nodes from the users, right? Then I'll say give me some edges as well. Okay, edges. Then I'll say for all the edges, right, I need to do something. So what I need to do, I want to ask you 3 variables or 2 variables, u and v. You need to give me the node u from which we are connecting v, right? And also in the previous video we already talked about unidirectional bidirectional graphs. So this would actually be a unidirectional graph. Cool. Okay, once the user gives us this, we'll have to have a data structure wherein we can store all this information. So I'm going to take an adjacency list for this, a digits list, and it's of size nodes, right? Then we'll say, okay, so just connect u to v. Cool. So this by this your graph population is complete. Now let's look at how do we take a queue. So taking a queue is pretty simple. You just take a queue like this, and you can push the root element. Now I'm assuming that the root element over here is 0, right? And then we'll start our structure. So while not of q dot empty, what we need to do is we'll firstly take size, right, and then we'll say till the size till there are nodes, or in this particular nodes I'll have to do something, so I'll have to process.
Size will be q dot length
Yeah,
now.
right. Q dot size. Okay, so my node would be q dot front, right, and I'll pop it, right. Always remember to pop it first, because sometimes you actually forget it and it's not even gonna show you the error, because it's simply gonna state it's a TLE. So that could get messy sometimes. So always try to pop it as soon as you have the value, right. Now what I'll do is I'll check for its neighbors, right. So let's call them neighbors in AJ list of node, right, and I'll push them. So I'll check if they have been visited or not. If they have not been visited, if the neighbor has not been visited, then only I'll be doing this, right.
Acha,
Huh?
q dot pop returns the value now, the
No,
popped
no, no, no,
value.
no. Q dot pop doesn't return the value; it pops out the value.
Oh,
To get the value,
in
you have to
JavaScript it does,
yeah,
so
yeah,
we could
you're right.
use that.
Yeah, you're right. In JavaScript it does. Over here it doesn't, as far as I
Okay.
remember. Cool. So now we have a visit area also. We have to take that. So while bool, let's call it visited, and the size is nodes. The initial value is 0 because we have not visited anything as of now. As soon as you visit something, mark it as visited, right. So one more thing you can actually do is over here itself mark it as visited. So cool, I'm marking the sources visited. Now I don't have to do it over here, but I can do the same over here. Okay, visited NV equal to 1, right. Okay, so this looks fine to me. I think this should kind of work. Let's provide it some inputs. Let's provide it with inputs like number of nodes we are expecting is 4 or maybe 3, right. And in these 3 inputs named 0, 1, 2, let's say 0 is connected to 1 and 1 is connected to 2. Make sense? Let's try to run it. Okay, we didn't get any output because we had not printed anything. Let's try to print something. And one more thing, so it's a level order traversal, right. So over here when you'll enter, so you'll be at a current level. Let's also print that level. So initially the level is 0, so we can print the level over here. See out. Okay, you are at level. Cool. And over here you'll have to print the value of the node. So the node val is node. I hope this makes sense to everyone. Let's try this now. Okay, so okay, it requires me to expand it. Okay, so initially you are at level 0, then your node value is 0, right. But after that it doesn't do anything. Now why is that the case? Okay, so here you had to also provide the number of edges. And also over here, so once you have printed the level and you have like used all the nodes, let's increase your level value. So it went to 0, right. From 0 it went to 1. So initially it said that you are at the level 0 and the node value is 0. Then you came to the level 1 and your node value was 1. Then you came to the level 2 and your node value was 2. Okay, let's try to say that both the nodes 0, both the nodes 1 and 2 were connected to 0 itself. Let's try to run that. So if you do that, you say it says that okay, you are at level 0, your node value is 0. Then you came at level 1, and at level 1 you had 2 nodes. That was node 1 as well as node 2, right? And if you want to add some more edges, you can do that as well. So we can say there was one more edge. Let's say one was actually connecting 3. Let's try that out. Okay, so you were at level 1, node value was 1. You went at level 1, your node value is 1 and 2. At level 2, your node value is 3, right? You can keep playing with that, but the answer won't change. So that's the thing for BFS traversal. I hope this was actually pretty easy, right? Any doubts in this? Because Dijkstra is actually based on this. If you are able to understand it, Dijkstra won't be a tough thing to understand. Any doubts so far?
Nope.
Okay, I hope everyone's cool with that. So let me move ahead. Now let's try to understand what Dijkstra is. Now over here, if I had an unweighted graph, right? So unweighted graph basically means that all of the nodes, let's say, only have a single same weight. So every node has the weight 1. Let's assume that. Unweighted graph doesn't actually mean that, but let's assume that every node has the value 1, or every edge has a weight 1, right? So I can say that if I want to go from the root node, let's say this is the root node having the number A, or the label A. I want to move some to some other node, right? Let's say X. Then technically its distance would be the number of edges that are present between A and X, right? So I can say if I want to go from A to X, the distance is 2. And if I just want to tell the distance, then I can simply use the algorithm that I just made in BFS, right? And over here, I'll be able to check that, okay, if you're coming to a particular node at a level 2, then basically your distance from that from root node is 2 itself. Well and good enough, right? Also, one more thing over here is that this is not the standard implementation, so no one would actually ask you to go in this sort, checking level via level. But I try to use this and I'm trying to explain this because this helps in a lot of scenarios. So people tend to get confused when they are asked for like doing a level or traversal and telling you and showing the levels that are present, and they start using Dijkstra and all that stuff over there when it's not even required. So just wanted to show you that how you can go level via level, right? Okay, so over here you can easily say that, okay, A to X, the distance is 2, but now the thing changes, right? So let's say this was also a node, still the distance remains 2, right? And let's say this was a node, right? Still the distance remains 2 itself, that doesn't change. But now if I make them weighted, or if I change their weights to some non-1 values, right? So let's say I call this distance is 10, this distance is 12, this has maybe 2, this has 4, right? And this is 3. So now I'll ask you, what is the minimum distance from 0 to X, sorry, from A to X. So we'll say this route is actually taking me 22 units. But if I take this particular route right over here, then it's just going to take me 2 plus 4 is 6 and 3 is 9, right? So the answer becomes 9 itself. Although the number of edges present between A and X are only 2, but their cumulative weight is becoming 22, that is greater than the cumulative weight of the path wherein 3 edges were present. So the point is, how do we solve this? Now, very easy thing to do over here is we can utilize the same logic as we did earlier. The only thing we are going to change is that rather than taking rather than using a queue, we can use a priority queue. Priority queue, or we can also use sets. You can use whatever you want, right? So I hope everyone over here is familiar with priority queues or sets. Is there anyone who's not familiar with these concepts? I'll explain them in brief if that's required.
Priority queue एक बारी like थोड़ा सा बता दो.
Okay.
I forgot what it was.
So priority queue is just a max heap or a min heap. The way you'll define it would differ, right? The only thing it does is that you can insert an element into it in order of log n time. You can remove the highest element or the biggest element from this in case of max heap, and the smallest element from it in case of min heap in log n time as well. And this data structure is always sorted. It's not completely sorted, but yeah, the max heap would always tell you the maximum element present in it, and the min heap will always tell you the minimum element present in it. It's similar to sets, so sets also have the same configuration, right? Make sense?
Yep.
Okay, cool. So we can utilize this. So I can say that this was my queue structure. So this was the queue I was in, right? Or this was the queue where I said while queue not empty, you need to process the queue elements, right? Over here itself, I'll say that, okay, I'll do the same thing, but instead of a queue, I'll take a priority queue. But how would that help me? So in my priority queue, I'll take 2 elements, right? Instead of just taking a single variable. So over here, okay, in the code, we were just taking the node value, right? In the queue, I was just taking one variable and I was putting the node value over here. Instead of just putting the node value, what I'll do is I'll take a pair and I'll put the distance, right? And the node number or node label, right? I can use 2 things over here. So when I'm putting the distance as the first element, and my data structure is something that already sorts everything, right? So if it's sorting it, then the least distance would be present at the first stage, right? So what this would make me do is that if I'm running it on a priority queue or a set or anything of that sort, then technically after performing all of these operations, I'll be able to get the minimum distance from root to all other nodes. Now, if this doesn't sound familiar, or if this doesn't sound comfortable or a bit weird, don't worry. I'll code it up along, and then it will make much more sense to you. Cool. So, any doubts in this? I'll definitely code it up. But any doubts in this, like what's happening over here? And there's one exception where you cannot use it. I'll explain that after I've coded it up and I've already shown you how it works. So meantime, if you have any doubts, you can straight away speak up so that I can help you out with that. Cool. So I already have the graph. No need of changing that. Let's change the other things. Instead of a queue, I want a priority queue. Okay, priority. Okay, spelling mistake. Priority. Yeah, seems fine. Okay. Also, we need, so by default, C++ actually gives you a max heap, right? But you need a min heap. So in order to make a max heap, because you want that the first element should be the smallest, right? So in order to make it a min heap, what you can do is you can say vector n, right, comma greater n. So this is not something I can explain because this is the standard template. But basically, whatever you are taking over here, you are taking a int, right? Let me just take a pair int because we don't want it to element. So whatever you take over here, you need to pass that along to other to these two things as well. If you're using Java or Python, the implementation is going to be different. So please take a note of that. Okay, pair. I have that fine. Yep, looks fine to me. Okay, anyway, so initially we'll push the value 0, right? We'll say it has a distance 0. That's fine. We'll now make a distance vector. Let's call it this of n comma index. Now, what's this distance vector? I'm saying that this distance vector basically denotes the distance from the source node, that is the node 0, to all the other nodes. But the distance from the source node or the node 0 to node 0 itself is 0 itself, 0, right? So we'll mark it as 0. Okay, give me a second over here. Yeah, got it. Okay, I think that solves it. Okay, yeah. Okay, so yeah, that's it. Now what I'll say is distance is done. I don't need the visited array over here. I'll tell the reason in a while. Then I don't even need these levels. Okay, let's remove this. Also, while taking, now we are talking of a weighted graph, right? So we'll also have to take the weights. Now also let's take the weights like this. Right. Now when you are storing the edges, so you are saying that okay, from 0 or from A you are going to B, but you also have to mention the weight, right? So we have to store that weight as well in the adjacency list. So let's use a pair of intent to store the weights and the edges, right? And I'll store it as v comma w. So the node followed by the weight.
Sir,
Bhai.
sir, is there anything wrong if we are using pushing the weight negative in the queue
Bro, your voice is breaking. Can you comment
and
it?
using that is with anything like that? And
Abhi, your voice is breaking. Can you comment it?
okay, right.
Cool. Okay, meanwhile I'll keep coding. Okay, over here, what I'll say is till that there's some element in the queue, I'll definitely have to process this, and the element, there would be two elements, right? So there would be node value that would be at the front. That's actually the second value itself, right? And the other would be the weight. Now the weight would be given by the second element. Okay, so the first element, sorry. I mean, that makes sense. Okay. Okay, it's top actually. In case of priority queue, it's actually top, not front. So yeah, top. Okay, Abhi commented, can we use the input with negative so that we don't have to use a greater in PQ? Yeah, you can do that. No, there's no harm in that. You can actually do that. And I try to do that in case of CP and stuff. But eventually, as you code, it becomes, it's more intuitive to code in this way. But even coding it, like taking the negative values actually makes more sense to me. I'll say it saves a lot of time. So if you were not able to understand what Abhi is saying is, No, we can do that, bro, with the extra. What you're saying is probably you're getting confused with negative weight cycles. No, negative. No, he's not talking of negative cycles. So if you are like marking everything as negative, right? Then technically your negative cycles will becomes positive. So the reason you are getting confused is what Abhi is saying is that since you are using a min heap, sorry, a max heap over here, or by default we have a max heap, right? So if you mark all the weights as negative, then this would become a min heap. So if okay, so in case of a max heap, the first element you're having, right? First element is maximum. If you make min heap, the first element is minimum, right? That's what he wants to leverage. So he'll be using a max heap itself, but the values would be negative, right? Does that make sense? Okay, if I have, yeah, so what? So that's different. You are basically getting confused in that. So if you have 2, 3, 5 in a cycle, right, and you're considering a min heap, then he'll say it's a negative cycle. But over here, he's just changing the values. Zoom the screen, sir, a little bit. Sure. Okay. Let's do one thing. I don't know what your actual name is, AD10 is, but let's do one thing. Let me complete this. Are you only changing the values within the heap, not the graph? Yeah, exactly. We are only changing the value within the heap, not the actual graph. Cool. If you still have a doubt, we can discuss. Yeah, cool. Okay. So if any of you didn't understand what Abhi tried to say is that he'll use a he'll use the max heap without actually doing all of these things, but then the weight he'll be pushing onto the heap would be negative. So that would make the same thing. So either you want the minimum element at the first, right? Or you make them negative and say that, okay, give me the maximum element. Okay. Anyway, let's move ahead. So what we'll say is, I want the node value and the weight, right? So I took that from the priority queue. Then I'll say let's remove it. Pop. Then I'll go for all the elements in its adjacency list. So I'll say ampersand node, the adjacency list of node itself. Okay, node is already used. Let's use some of the elements. Let's call it X, or we can call it neighbor, whatever you want to call it. We'll say that if, okay, did we do some trouble over here? PQ is undefined. Okay, we used a Q. No worries. Okay. So if your distance, right? If your distance of X is greater than whatever weight you are having, you have two elements, that is X and we have W, right? So what's X? X is the node that you're going to. So X is the node B, right? And W is the weight you require to go from A to B, right? And the weight over here is actually A1. Makes sense? Okay, so what you're saying is if your distance, which you currently have for this particular node X, right? Okay, yeah. If your that distance is greater than weight plus W, right? Only then it would make sense to use weight plus W instead of distance of X, right? So you'll say distance of X is equal to weight plus W, right? And you'll have to push this thing also onto the queue. So you'll push X, and then you'll have to push the entire thing. So distance of X. Make sense? At the end, once you have performed all of this, you can be sure that your distance array contains the best values possible, right? So you can say that I want to print the distance. So you can say this, okay, distance, cout d, right? Okay, good enough. So over here I can say that I'm having three nodes. From 0 to 1 the distance is 2, so from 0 to 2 the distance is 1, and from 1 to 3 let's say the distance is 4. Let's try to run it. Let's see if it fails somewhere. Okay, so it says that I can go from 0 to 0 in distance 0, that's fine. I can go from 0 to 1 distance 2, that's also fine. I can go from 0 to 2 in distance 1, that's cool. I can go from 1 to 3, oh sorry, 0 to 3 distance 6. Now why is that the case? You will go from 0 to 1 in distance 2, and from 0 to 3, right? Or from 1 to 3 you'll go in distance 4. So 4 plus 2 is 6. That makes sense. Let's try to introduce some cycles also, so that it makes more sense. So I'll say I can go from maybe, okay, from 2 to 3 I can go in distance 5, right? Let's see what happens now. Okay, input is wrong. I have to change it. Yeah, over here you are having 4 edges. Okay, so again the thing remains same, because over here you did introduce one extra edge, right? That was this thing. Let's remove this. Yeah. Okay, so you did introduce extra edge over here. So you said that okay, you can also go from 2 to 3 with a distance 5, but since it had a better answer, so it would always prefer that. This makes sense to you? This was the entire Dijkstra. So this is the Dijkstra algorithm. It's not that complicated. It's a small code, really a small code, I'll say, right? So this is the heart of the Dijkstra algorithm, that you have to save the values, right? And then you have to say that you will only be utilizing this particular edge. Actually pushing something on the queue right over here would mean that you're utilizing this particular edge, right? So we'll say you only utilize this particular edge if it's benefiting you. Now what do we mean by if it's benefiting you? If it's gonna decrease your distance, the distance it's gonna take you to reach from the root to the X node, if using this particular edge is decreasing that distance, then only go with it. Else don't, right? Or else continue. Okay guys, so make sense? Or okay, how to do that in CP? Is there a better alternative? Yeah, so I'll come to that, but do you guys still have any doubts over here, or shall I proceed ahead? Okay, yeah,
No,
cool.
sir, all good, sir.
All good. Yeah. Okay, so what happens generally in CP is, because this particular approach is required because you actually want to check for negative value also, right? Okay. But before I like explain you that, let me give you a edge scenario, right? So let's talk of edge scenario. So let's say that this is the graph I'm having, right? This is the graph, right? Let's say this is 1, this is 2, this is 3. Let's say the distance from 0 to 2 is actually 10, right? The distance of 1 to 2 is 1 to 3 is actually, let's say, 4, right? And then the distance from 0 1 from 2 to 4 is maybe like, okay, 2 to 4 is like 1 itself, right? The distance of 3 from 3 to 4 is probably 100, right? Now let's just make it zero based indexing. So in zero based indexing, this would become 0, 1 would become 0, 2 would become 1, this would become 2, this would become 3, right? So now what would happen is that initially I would go from here to here, right? I would go from this node to this node. So I'll say good enough. Distance I have is actually, distance of 2 is actually 4 itself. From here I can have 2 edges, so I can go to here or to here. So I also say that okay, I'm pushing my pushing 3 onto the queue, and for 3 the distance would actually be, okay, so the distance of 3 would actually be 104 itself, right? It will also come over here, right? And this node also would be there. So for this particular node, for 1 you will be having 2 distances. Distance of node 1 would be 10, or you can say it would be the minimum of 10, comma. So let's say this particular distance was something like maybe 5, right? So it will say that the distance of from 2 to 1 is actually is 5, and from 0 to 2 was 4. So this is minimum of 10, 9. So distance of 1 would be given by 9, right? And as soon as that happens, then in your next iteration, you realize that if I can go from 1 to 3 in this particular path also, if I follow this particular path, then my distance will be 9 plus 1 equal to 10. Now, had you followed the BFS approach, you would have simply said that, okay, this is the smallest path I can go from, so I can directly go from here to here to here to here, right? And then you would have got a wrong answer, because you would have said that the minimum answer is 11, which is clearly not the case. The answer over here is 10 itself. Make sense? These are the scenarios where it's helpful. Now where you cannot use it, so you cannot use it wherein you are having negative cycles. So what happens in case of negative cycles? And I guess someone of you actually got confused. Yeah, so AD10S got confused over here. So in case of a negative cycle, let's say this node is going over here, this is becoming a cycle, right? Now how would I make it negative? Let's say this has a weight 10, that's fine. this has a weight -9 and this has a weight -2. Cool. So what will happen is that if you perform this entire cycle, so you will be performing -1 units of work. So every time you perform it, your work actually decreases. So technically there's no stopping to this. You'll keep performing this, right? So this is where it's not helpful, and you should actually avoid it. And so yeah, that's it. So Abhi had the point that how to use the CP. Is there any better way? What I'll say is that in CP, most of the times you're actually not required to find the distance from a node to all the other nodes. Most of the times it's just about finding the shortest path or finding the best alternative to reach a particular point. Also, okay, and also there are no negative edges. So in CP case in general, I'm trying to generalize it, don't consider that this would always happen, but this would happen most of the times as far as my observation goes. So in CP, the first condition you actually see is that edges are not negative, right? And the second condition is that from source to X, this is what you need to do, right? So a better way of doing it would be instead of taking, you can actually remove distance from here. Distance is not even required. You can rather use a vector bool visited. You can use that. Initially you'll say that okay, visited of 0 is 1. Okay, so even this kind of case is not required. You'll simply say that if visited of X, if X is visited, then don't do this. If X is not visited, then do this. Over here, just mark visited X equal to 1. Not over here, but over here. Visited of X equal to, okay, visited of node equal to 1. Okay, remove this. Okay, you have nodes. And distance is not required, so you can remove that again. Okay, over here you just need to add the weight plus W. Yep, that's how you do it in case of CP. This makes sense to you guys? Guys,
No, sir. Kindly give one example.
okay, cool. Let's say, okay, should I draw the graph? Okay, so let's say this was the graph.
No, any vector will work.
Any vector would work? What do you mean by that?
Graph is not needed.
Okay,
I
so
am saying that.
okay, so the basic idea over here is that since you are not having negative edges CP, right? In most of the cases, you're not having negative edges. Also, you're not asked for to populate the entire graph, that what will be the distance to go from A to B and from A to C, or to all the nodes from the source node. That kind of questions are not generally asked, right? So what you can do is you can start from the root node itself, right? And you can just make a variation of BFS. So it's somewhat like a variation of BFS and Dijkstra. But the code is a bit shorter, so I prefer this. So what it does is, okay, give me a second, let's just clean up the code also so that it's easier to understand. So what I'm doing this particular code is that initially I'll take the node and the weight that actually is required. I can't get rid of that at least, right? Then I'll pop the node out. I'll mark it as visited, right? Then I'll go, I'll check for the adjacency list. I'll say that if it's not visited already, then push it. Now, how does this matter? Now, in case a node is visited, right? So if your node was visited, then technically that means, and there was no, so the point over here is that there are no negative edges as well. So if your node was visited and it's a priority queue or a set or some data structure which has the smallest element at the first, right? If it's that kind of a data structure, that means your lowest weight has already been processed. So if let's say you processed a node A with weight, so by weight I mean this particular value, right? With weight maybe 10, right? And then you keep processing it. Now when you'll process it for some other node, or when you'll run this iteration for some other node, then it would never happen that you'll be having a value that is less than 10. So you cannot have a value 9. Obviously you can have a value 10 or above over here itself. So if you have already processed a node over here, right, that means you have already received the minimum weight for that. So if that is happening, so over here you can say if your node is equal to node destination node, just call it destination node, right? Node, then return answer Proceed. Because after this, after performing any amount of steps, if you've already reached the node, right, then after performing any number of steps, you will not be able to decrease the weight further because you're not having negative weights over here. So your weight is always going to increase or going to remain the same in every iteration after the ith iteration. Makes sense now?
Yes, sir. Means that, sir, if any node is if the output node is already taken out from the periodic, then that is the result
Yep,
final.
yep. Because after that particular iteration, it can never be the case. So after any I iteration, right, it can never be the case that your weight actually decreases. It's always gonna be increased, right, or it's gonna be the same. So as soon as you hit the hit the node in the priority, you can say that you already got the answer. So I don't know about how if you'll be solving these kind of questions in code forces or code chef soon enough, because these kind of questions come at a far high level and they are too very complicated. But these questions are frequently asked in lead code, and this can actually help you a lot. Because whenever I solve lead code kind of question, I always use this approach, and this works wonders because the code is actually shorter. In contest, it actually matters a lot if you are able to reduce your code by a few lines, because it this actually increases by that, right? And it's more intuitive as well. So this helps a lot, and I don't think there was a good editorial also on this. So I just wanted to explain you this logic also. Make sense? Guys, any other doubt?
Yes, sir.
Any other
Thank.
doubt?
Overload for me.
Overload for you?
Yeah.
So I'll suggest you one thing. This particular video, right? Just I'll as soon as I upload this, watch this video, right? After that, I'm suggesting you one question, right? This is a pretty interesting question. This is a hard question, and in the contest, 498 people are able to do it, right? I'll suggest you go through this question. Now,
Okay.
this question just requires DFS. I'm just gonna ping it. Okay, so this question just requires DFS, sorry, Dijkstra, but along with Dijkstra, it requires a small observation. It's possible that it will take you long to get to the observation, but if you're able to do this, then your concepts would like it would be sure that your concepts are great. Make sense?
Okay.
But up till BFS, you were able to understand the Dijkstra part went
Yes.
became a bit
That
difficult.
the Dijkstra bar. Whatever it's
Yes.
pronounced.
So yeah, Dijkstra. I'll just advise you to try it once again. Right? Try this code. Watch this video and try to dry run the code once or twice. You'll be able to understand it definitely.
Okay.
Cool enough. Anyone has other doubts, or if someone felt that it went a bit overboard, or could actually advise me some improvements. Cool guys. If no one has a doubt, okay. Few people are typing. Can you link an article? What do you need an article for? Using PQ for Dijkstra. Dijkstra, you can use anything, right? You can use PQ or a set, it doesn't matter. So the thing remains exactly the same. Is there a specific doubt you're having, A10S? एक तो भाई नाम बता दे यार, A10S seems so complicated to speak out. Wait, PQ you suggested for what then? You can call me Adiha. Okay, cool, Adi. So the thing is that when I talked about PQ, I said that you can either use PQ or you can use set. It doesn't matter. And the other thing I showed you that had a few lesser line of codes, right? That thing is, I don't think there's an article on that. So that is something I automatically started using, and that is something I wanted to teach you because it just has a few lesser line of codes, and I found it, useful in contest. So that's it. And I've already mentioned this particular question. I expect you to go through this question at least. I already have a video on this as well, but I'll advise just go through the question without going through the video itself and try to solve it on your own. TLE on pretest 2, Jugai, were you able to solve this question? Like after the contest, were you able to solve this?
Yes, I did absolve it.
Okay, did you find it interesting? Was it tough? How was it?
Yeah, it was tough, but after I understood the logic of Dijkstra, it was easy.
Okay, cool enough. So yeah, cool enough, guys. Please do this question and ask me if you have any doubts. And if you think the things are getting a bit tougher to understand, or if I need to explain the things a bit more, let me know. You can let me know right now, or you can just ping me offline or on any of these groups. Probably ping me on off topic. Cool, guys. Thanks a lot. Bye bye.
Bye bye.
Bye.